Okay. So we are doing calculus day 10. And hopefully we'll be able to finish up calculus here soon. Looks like I just have a few more concepts to go over. And then I'll get some practice in for each of these things till I feel confident. And we'll just go in and, take the test. Perfect. So I think we'll go through the Anki first, and then we'll try to hit as many of these points as we can tonight. Actually, I think it's probably likely that I'll be able to get through I think I'll probably be able to get through these tonight. So we'll probably end up starting to practice. So that's excellent. Okay, so I think we'll just get started here. Okay, this is the type of function where it specifies the conditions under which a particular function is used. Okay, intervals or conditions. Perfect. The mean value theorem. This is the idea that for a function that is continuously that does not break on a closed interval and is differentiable on an open interval, that there is a derivative, a point whose derivative slope is the same as the slope between 2 points. I guess put simply, for a given function where 2 points are specified, there is a point between the 2 points whose instantaneous slope matches the slope between the 2 original points. And then we do have some conditions for that. I just realized I'm not sharing. So that's the mean value theorem. Okay, and then so this would be something like this. So we have this function here. We choose a point here and a point here, and then we draw our slope. So what this says is that there is a point here that has the same slope it matches, it has the same slope between the two. So okay, perfect. So there's that one. It's continuous on closed and differential on open, I believe. We're actually going to run into the open and closed. So, okay, so closed interval is, let's see, that include the endpoints A and B. Open, exclude endpoints. Okay. We're going to just remove these unnecessary asterisks. Okay. So square brackets include, parentheses exclude. Okay. Do I have... It seemed like I just had the same question there. Oh, the syntactical difference. Okay. So this is closed or square brackets, and then, okay. I was thinking that I had the same question, but the first question was slightly different. For the mean value theorem, why do we need to be continuous on a closed interval and differentiable on an open interval? Continuous on a closed interval, because if it weren't the case, then we'd need to, or there could be a situation where the the instantaneous slope that we have that matches the secant, or I guess the slope between the points, it could be non-existent. So if like this point didn't exist on the function, then this couldn't be certainly true, right? If like we didn't have any, if it wasn't continuous there. And then differentiable. So I'm not 100% certain, but we need it continuous such that the output is there, but also, or I guess the input and output is there. The output. Output is there. Also differentiable, such that we could like, so I guess the two conditions are that this piece exists right here. This piece exists right here for this point, and that we could differentiate along this whole thing, right? Such that this instance of a differentiation works. Okay. Okay, so in the tangent line is here in the mean value theorem, and the secant line is here in the mean value theorem. Euler's number is a constant that is used for like natural processes of growth and decay. Yeah, it's often used. I'm going to do that again. I'd like to know that it's 2.7. Second order derivatives are derivative of a derivative. This is a piecewise function. Euler's number is, I'm pretty sure I just... Oh yeah, because I just resent it. Okay, perfect. It says 2.7. Nice. Oh, we'll pop that back up. Okay. So now we'll just kind of keep going. And then we will hopefully... I'm hoping that I get through all the conceptual stuff today. Here we are. So I did talk about what I thought might be the case for how quickly I would need to, or I'd be able to get through the rest of calculus. And I was surprised in the fact that it seems like it'll be less time than I thought. I said I'd be surprised if it was less than 4 hours and more than, I think it was 20 or more than 10, I believe, 15. And so I overestimated all this. I overestimated that which is new. So after I learned those like core concepts in calculus, then I'm able to get through all this. Obviously, I need to do the practice bit. But since I have a strong conceptual understanding, I don't foresee myself having much of an issue there. So I guess this raises a question about like the learning strategy that I used, right? So I pretty much entirely came to calculus from the conceptual standpoint, and have learned, quite a bit of what would be considered calculus 1. But I haven't done any practical, like, if I were at this point in level of understanding for taking a class, I would have done like loads and loads of problem sets, right? So that's interesting. Fourth, I think, well, I don't know. There are some things where it's like you absolutely need the like practice with it before you understand it. But I assume like with things like this, where I was able to understand before I began practicing, that I don't know, I think I'm fine. Or at least it went pretty well. Yeah. Though for like higher mathematics, it may be that you just like, I don't know, you probably just can't wrap your brain around it until you've really worked with it, So, who knows? Okay, so, we're here on what are inflection points and how to find them. So I believe inflection points are where, oh, I think I actually already covered this, where it goes from convex to concave or concave to convex when it changes. So how do I find inflection points in, for a function in calculus? Okay, so we compute the second order derivative. We set the result to be 0. Oh, okay, that makes loads of sense. Okay. I think before I didn't get this at all, but now it's almost entirely clear. So say we got oh my, say we got the wiggly boy here. And so each of the points where we're changing from convex to concave, there'll be a point on that where the slope is 0. Yes, okay. Okay, right. So we could say at this point here, at this point here, there's going to be a line, or with 0 slope. And at this point here, there's going to be 0 slope. We'll say at this point here, it's probably a little bit before that, but each of these points would be points where the slope equals 0, right? And okay, so this is exactly right. So we have to take the second order derivative. Because it could be the case, let me take a counterpoint. So it could be the case that my function is like this. So the issue with this function, we'll go blue. Oops. Oh my heavens. The issue with this function is that my slope is never 0. Right? So even when I go like this, I'm still... Oh, actually. Okay, so you could call this point 0 here and this point 0 here, right? I'll draw an even better example. So we'll say that my function went like this. It's okay, so it's clear, and okay, these wiggles are intended. It's clear that this function has inflection points because at this spot here, and this spot here, and this spot here, and this spot here, and I don't know, this spot here maybe, we're going from convex to concave, right? But the issue is that we don't ever have 0 slope, as we would have if the convex mapped perfectly with the actual slope of the line. But that's not the case. But we can measure the rate of change of the slope. Or so I guess, yeah, the rate of change of the slope. Or no, let's see. This is the derivative of the derivative, right? The second order derivative. And this could be thought of as the instantaneous rate of change of the rate of change. Right? Okay, so we'll go here and we'll go pink. Okay, so at So I'm gonna map out the. So we're gonna map out like this section right here. That'll be we're gonna map out. We'll say this section of slope. It's gonna be right here. And we're gonna zoom in a bit. Okay. So so we are first. Actually, I don't know how closely this will like map onto it, but say we're going. Okay, so. Okay. So we'll say that. So we start. Well. Okay. So we'll say that we go from a slope of 2. We go from. We'll say we'll go from a slope of 2 to a slope of 1 to a slope of 2 to a slope of 1. Okay. Yeah. This is it. This will be an easy way to explain. So this is the describing the. Like this is the mapping of the derivative and how it goes. So we go like this. We have a function that goes from the slope of 2 to the slope of 1 to the slope of 2 to the slope of 1 to the slope of 2 to the slope of 1. Okay. And obviously this is not a perfect mapping here. So we do still have the issue. Well, okay. So now it is mapped nicely, like our initial example, where we could take the rate of change at our points here, and these are all equal to 0. And so when we have the second order derivative, because the second order derivative is the rate of change of the rate of change, when our rate of change goes from increasing to decreasing, our rate of change will hit 0 at some point. Inversely, if we go from decrease or increasing, I don't know if I said increasing to decreasing or decreasing to increasing. Anyway, if we flip-flop between increasing to decreasing, if there's any variation there, then for our second order derivative, being that it's the rate of change of a rate of change, it will be 0 at those points. Yeah. Okay. So I got that. Okay. Okay, yeah. Inflection occurs if this changes signs, indicating changes of curvature from concave to concave to convex, concave up and concave down. Okay, how do you find math and calculus? Okay, I do need practice finding inflection points though, because I think that would be good to do. Okay. Perfect. How to integrate using Riemann sums. Okay. What's the benefit to integrating over Riemann sums? Is it when the function can't be turned into an antiderivative easily? Oh. Okay. So the reason why I asked that question is that Riemann sums seem to be like more work than just using the power rule for finding the antiderivative, right? And so I wondered because, okay, so for this Riemann sum, what we're doing is we're finding like intervals and then we're using our information about those intervals. I don't know if we're calculating them separately. I think this is pretty much the equivalent of using the little like is like finding the area under the curve through finding the area of all the little boxes under the curve. So if we just like make little boxes here, I think this is like in all like practically speaking, this is what a Riemann sum looks like, I believe. And then we approximate it using summation, meaning I think we're just like adding up each of these little boxes. And then we say, hey, we got like this answer, you know, blah, blah, blah. And so, yeah, I believe that's how it works. And then if you wanted to get more like a better approximation, you would just need to add like more of these little boxes here, because as you add more and more boxes, then it becomes like more and more correct. And then actually, so one question I have is like for these yeah, so if it is if my intuition or like if my understanding is correct here, then for these boxes, I don't know like where the tops of the boxes would be. Is it the right side of the box that always like touches this guy? And so we have like an over approximation, right? Or is it the case that or is it the case that like we take it from the inside edge, right? So alternatively, we could go like this, where the left edge or the instead of the right edge touching the line, the left edge touches, and then we'd be under the actual amount. Okay. Well, actually, I'm not sure if that's correct. We'll see. I think I might do just a quick video about, is it Riemann sums? Okay. And then we use Riemann sums when it's either like a mathematical impossibility to use to just calculate the antiderivative, or if we don't have a nice algebraic function but only have empirical data points. Makes sense to me. Okay. I think I'm gonna watch a video about this though, because I do. Dang, this organic chemistry teacher, he is literally at the top on every calculus video that I've looked up. It's actually impressive. Oh, hey, so looks like we do. It looks like this lady is going to be telling us the difference between the left and right, and how it's going to be over and under. And it looks like that distinction is made.
There are 20 days left until the AP Calc exam. Let's talk about Riemann sums. We need to know 4 types of sums for the AP Calc exam. Left, right, midpoint, and trapezoid. A left Riemann sum means we're approximating this area using rectangles, where the height of each rectangle is determined by the height of the function at the left endpoint of each rectangle. A right Riemann sum is a rectangle again, except this time the height of each rectangle depends on the height of the function at the right endpoint of each rectangle. Looking at these two functions, you might assume that a left sum is always an underestimate and a right sum is always an overestimate. That only holds for increasing functions. Let's look at a decreasing function. Now we see that the left sum is overestimate and the right sum is underestimate. Now what do you do when things get negative? You still find length times width. When you sum everything up, you treat these rectangles as having negative area. And one last piece of advice, make sure you know your left from your right. There are 20 days left until the AP Calc exam. Let's start.
Now let's say if we have the graph of y equals x squared. Let's focus on the right side of the graph. How can we calculate the area under the curve from, let's say, 0 to 8? So how can we determine the area of the shaded region? Now, one simple way in which we can do so is by using rectangles. So let's use rectangles. Let's actually use 4 rectangles to approximate the area. And there's 2 ways to do so. You can use a lower sum, in this case which will be the left endpoints, or an upper sum, which will represent the right endpoints for an increasing function.
I'm just going to see or have it walk through the evaluation of a Riemann sum. A Riemann?
To stay tuned, so let's go through the different pronunciations. In German, it is usually pronounced as Riemann.
Riemann. Riemann. Riemann. Riemann. Riemann sum.
Riemann.
Riemann.
Riemann. Riemann.
Riemann.
Riemann.
Okay, Riemann sum. Okay. Okay. I think I have a point on Riemann sums. Oh, I accidentally did the wrong one here. Okay. So, we'll just move this guy down here. Okay, we already have that. And I assume local extrema are this same as inflection points. Because inflection point would represent the highest or lowest point that it arrives at. Well, yeah, necessarily. Um, oh, no. Okay. So, okay. So that's incorrect. Um, okay. So it looks like there's a first derivative test and a second derivative test. Okay. Oh, okay. So here it is the case that, wait, is less than 0? Is greater than 0? Local minimum. So I think these would be swapped, right? If the result of this is less than 0, that means my slope is the rate of change for my slope is negative. I don't understand that. We'll look at we'll look at local extrema. I will also check what is the linearization of functions. Calculus. Okay, linearization. Let's see. Linearization approximates a function f of x near a point x equals a using the tangent line. Approximates a function. This simplifies complex functions locally, providing easier computation and insight into function behavior close to a. Okay. Let's see. Linearization. Okay, we'll look at this formula. So, approximates a function by its tangent line at point A. Okay, so f of a plus f prime of a, and then, so I'm pretty sure, So I have looked into some functional programming stuff. And so I'm pretty sure what's happening here is something called currying. So this, what happens is that f prime of x evaluates, f prime, function f prime evaluates at a, and then the result of function f prime is, of course, the, let's see. Actually, I don't think that returns us with a function. Because f prime of a returns the slope. So I'm not sure we can continue it. I don't know if we plug this into the slope to evaluate that, but how currying would work is, say we have a function that returns a function. I guess you could think of, well, I don't know. I don't think you could think of an antiderivative as returning a or is it the slope being a function? And so anyway, how currying works is that we have a function that like returns a function. And so we evaluate the first function based off this parameter, and then evaluate the function that emerges after this evaluation using the second parameter. Yeah. So I think we'll check out. Okay, so I think I'll need to look into linearization more as well, as limits of Riemann sums. Okay, this actually makes sense now. So for this one. So if we have like if we're doing like the Riemann sum or what, oh man, there we are. If we're doing the Riemann sum or whatever, like as the number of rectangles I have approaches infinity, then it becomes like the integral. Let's see. As my number of as it approaches infinity, it's no longer a approximation. Well, maybe it is still. No, I think it would not be an approximation. Okay. I don't think it would be an approximation. If we are going to integrate using Riemann sums, then if we set our limit to infinity, as we approach infinity, our Riemann sum approximation of the integral no longer becomes an approximation as it approaches infinity, right? Or will it always be the case that it is an approximation? I guess, actually, I think it will always be the case that it's an approximation, unless you are at infinity. Okay. Okay. So add that one. Has limits of Riemann sums. I don't know if this seems like an odd way to ask it. Okay. Okay, I'm not sure what this guy's called. But it seems like it is used for definite from definite integrals, meaning between these two things, or I guess from between this thing and this thing. Yeah. Yeah, I think that's correct. Okay. And then also I want to learn the syntax here. I've been told this is merely a for loop. That this is the same thing as a for loop in computer science or in programming. Used in the integral sign. Maybe I didn't, because now that I'm thinking about it, I'm pretty sure I'm pretty sure I captured this in AnkiCard before. If we sort by when it's due. Actually, I don't want to search through them all. Okay. I called it the integral symbol. Okay, so we should have that already. How are limits expressed? Context of the integral symbol syntactically. Okay. Perfect. Now, tell me about the summation operator. If it's called that, okay. What is the summation operator in mathematics? Doop-a-doo. I is the index variable starting at the lower limit 1 and increasing to the upper limit n. And n is specified here. Okay, I think that makes sense. So this is our starting index, or I guess the lower limit. And then we just increase let's see. We increase by summing them all. And then this is the ending one. Okay. Seems reasonable to me. Oh, doop doop. Okay. For this one, that's fine. And I think this one will just merely be a one we walk through, so. Let's see if it completes it here. Okay, so it looks like we just do some algebraic substitution with the trigonometry functions. Okay, so I need to do an overview of the trigonometry functions. I think I remember most of them. Trigonometry functions and Oncify. Okay. Still going. Oh, the reverse chain rule. Okay. We'll want to look at that. I heard about that. I have no clue what that is. Dang, it is still going. Yeah, they definitely have a thinking model under this one. Because it seemed to like be like, oh wait a second, let's do a different way. Oh, let's do a different way. Okay, so I guess the next time we're gonna do the reverse chain rule, we're gonna overview the trigonometry functions. And then I think I'll probably do L'Hopital's rule. And then we'll start just practicing. Yeah. And then we'll just kind of finish up after that. Or let's see, I think we probably have maybe 2 more sessions. Yeah. Sweet. So I think we will finish up there today. And I will see you guys probably on Monday of next week. Adios.